Everyone, Mary here, and we are going to do a couple Doppler example problems. So we're going to do two in this little video, so here goes. A car horn has a typical frequency of about 180 hertz, and I did look that up, so that's a relatively accurate value. A car is passing you, traveling at a constant velocity of 55 miles per hour while blowing its horn. What frequency would you hear while it approaches you? And then what frequency would you hear after it has passed you and is moving away? So let's look at part A first. So the car is moving towards you. You are the observer. Here's your little ears. And the waves are approaching you, and we want to know what frequency you're going to hear. Now, this is a Doppler problem, so we're going to use that Doppler equation that says the frequency observed is the frequency of the source, the velocity of the wave, plus minus the velocity of the observer, divided by the velocity of the wave, minus plus the velocity of the source. So in this first situation, the frequency of the source is going to be 180 hertz. The car is going by you at 55 miles per hour. That's the velocity of the source, is 55 miles per hour. And we have done this calculation or that conversion many times in the course. 55 miles an hour is 24.5 meters per second. And it's blowing its horn. What frequency would you hear? So I want to know the frequency that's going to be observed. The piece of information we do not have is what is the velocity of the wave itself. If you are not given any information about the velocity of sound in air, use 343. And through the homework and through test questions, etc., that is a commonly used value if you do not know the temperature for the speed of sound in air. So let's go ahead and put our numbers in here. It also says it's approaching you. Now, if you recall from what we've talked about in lecture, if the source is moving towards you, towards means you are going to use the top set of plus minuses. So we're going to write this out, and it's going to look like this. The frequency to be observed is the frequency of the source, 180 hertz, times the velocity of the wave without any additional motion, plus, because it's towards, the velocity of the observer. Now, the observer is not moving, so that's going to be a zero, divided by the velocity of the wave, so that's just the speed of sound, minus the velocity of the source. The car is coming towards us at 24.5 meters per second. And when I throw all of this in my calculator, now remember, order of operations is important. You've got to do the division has to be after you do this subtraction. So an intermediate step would be 180 hertz divided by 343 meters per second divided by 318.5 meters per second. And when I do this, I get the frequency observed to be 194 hertz. Now, with Doppler, always stop and do a reality check. Does that make sense? Well, you and I both know that when the source is coming towards us, the frequency is going to be higher. And so standing still frequency is 180. As it's approaching us, we get 194. So that's a check. Yes, it makes sense. Now let's go ahead and do part B. Part B wants to know what happens after the car has passed and it's moving away. What frequency are we going to observe? So the frequency observed is going to be the frequency of the source, velocity plus minus the frequency of the observer, minus plus the velocity of the source. Did I say frequency? I meant velocity there. I may have misspoken. Okay, the frequency of the source is still 180 hertz. That's the car horn. The velocity of sound in air is still 343 meters per second. But now the car is going away. And because the car is going away, we're going to use the bottom set of symbols. So this is going to be a minus on the top, and it's going to be a plus on the bottom. The velocity of the observer, again, the observer is standing still. Speed of sound in air is 343, and the source is now traveling away from the observer at 24.5 meters per second. And when I do all the lovely math, I end up with 168 hertz. And with Doppler, as I mentioned, always do a reality check. Does this make sense? Because the source is moving away, the frequency should be lower. And yes, 168 is lower than the standing still frequency of 180. So we're good. That's a good answer. Now we're going to immediately go do a second Doppler example problem. And I have this down a ways. So let me scroll down a bit. This time, we're going to have two things in motion. So here goes. Lady Gaga is out for a morning run. She's running eastbound, traveling at a constant speed of 15 meters per second, and is singing a note of 440 hertz. You pass her as you drive down the street, and you're traveling at 25 meters per second, traveling in the opposite direction. The temperature in the air that day is 21 degrees Celsius. I want to know, what musical note do you hear as you approach the divine Madame Gaga? So here we go. Here's the situation. Here's Ms. Gaga out for a run. She usually looks more elegant and glamorous than that, but she's going to be moving towards us at 15 meters per second, and she's going to be singing a note of 440 hertz. You're going to be in your fabulous car, traveling towards her at 25 meters per second. And we do not know exactly what speed the sound waves are going to have in air, but we do know the air temperature. So we know the temp is 21 degrees Celsius. And the question is, what is the frequency that is going to be observed? And you are the observer, and you are in your awesome little car. So same equation, frequency observed, frequency of the source, velocity of the wave plus minus velocity of the observer, velocity of the wave minus plus velocity of the source. Now this is a towards situation. You and Ms. Gaga are moving towards each other, so we're going to use the top set of signs. Now remember, if you just choose the correct pair of signs in the Doppler equation, you do not have to change the positive or negative either velocity when you plug them in. Let the equation do the positive and negativeness of the relative velocities, then you don't have to worry about it. And I kind of like not having to worry about something. All right, before we can do that, we have to figure out the velocity of sound in air, and we're going to have to go back a bit and use the equation for determining the velocity of sound. And the velocity of sound on a particular day is going to be equal to 331 meters per second times the square root of the temperature in degrees Celsius plus 273 to convert it to Kelvin, divided by 273, and that's going to give us our velocity of sound adjusted for temperature. So 331 times the square root of 21 degrees Celsius plus 273, that's going to convert this into Kelvin, divided by 273, which will be in kelvins. And when we do the math, and please watch out for order of operations here when you put it in your calculator, I'm going to end up with 344 meters per second. A slight difference, but definitely a difference. So I'm going to use that in this equation. I'm going to spool down a bit so I have some room. And here goes. I'm going to change pen color so we know what we're up to. The frequency observed is going to be the frequency of the source. Well, she's singing a note of 440 hertz. The velocity of sound on that day is 344 meters per second. This is a towards situation, so this is going to be a plus. Velocity of the observer, you're moving towards her at 25 meters per second, divided by the velocity of sound on that day, 344 meters per second. Towards situation means the bottom is negative, and her velocity towards you is 15 meters per second. Watch the order of operations. You do the addition or the subtraction first, then you do the division. When I do all the lovely math, I get 493 hertz, and that is the musical note that is going to come to your ears. So there you go. There's a couple Doppler examples. Best of luck with the homework, and we will talk to you soon. Bye-bye.